Hello, I am Peihao Chen from South China University of Technology. Today I am glad to talk about RSPNet, Relative Speed Perception for Unsupervised Video Representation Learning. Codes and models are available at my GitHub repository. First, I will introduce the background about unsupervised video representation learning. As we know, video analysis has been an important research topic in computer vision. It has various applications, including action recognition, action localization, video question answering, and so on. Most existing methods learn video representation following the supervised training paradigm. This means that they require a large amount of data annotations. However, compared to static images, it is hard to annotate the video data frame by frame because videos have a larger data volume. Recently, unsupervised video representation learning has attracted great attention. This task aims to learn video representation from unlabeled videos. Generally speaking, we will design some pretext tasks. These pretext tasks will generate some pseudo-labels for training a feature extractor. After pre-training on the pretext tasks, the learned video representation can be used for downstream tasks, such as action recognition, video retrieval, and so on. However, unsupervised video representation learning is very difficult because of several challenges. First, the downstream video understanding tasks rely on both appearance and motion features. Here, the appearance features indicate background scene, texture, and shape of objects. The motion features indicate the movement of objects. It is difficult to learn representation for both appearance and motion features simultaneously. Second, it is difficult to mine effective supervision from unlabeled video data for representation learning. So, an important underlying problem is how to generate pseudo-labels for training to learn both appearance and motion features. Existing methods attempt to solve these challenges by designing pretext tasks to obtain pseudo-labels for training. The pretext tasks include context prediction, playback speed perception, temporal clip order prediction, and so on. In particular, training models using the playback speed perception task achieves great success because models must focus on the moving objects to perceive the playback speed. This focus helps models to learn representative motion features. Specifically, SpeedNet train a model to determine whether videos are sped up or not. OOPS, PSP, and PACE attempt to predict the specific playback speed for each video. However, these works suffer from two limitations. First, the playback speed labels can be imprecise. This is because of the inconsistency between the motion content and speed labels. For example, the first two clips in the figure have the same speed label. But the second clip finishes the shooting action within a short time, but the first clip does not finish the action. This indicates that the clips with the same labels may appear different to each other. Also, the clips with different labels may also appear similar to each other. The underlying reason for this is that different people often implement the same action at different speeds. Using such inconsistent speed labels for training may make it difficult to learn discriminative features. Second, perceiving speed mainly relies on the motion content. The models are not explicitly encouraged to explore appearance features. However, these appearance features are also important for video understanding. To address the limitations mentioned above, we proposed two pretext tasks to encourage models to learn motion and appearance feature respectively. Specifically, given a set of unlabeled data, we sample a collection of video clips at different playback speeds. Then, we use an encoder to extract video features for each video clip. The encoder can be any neural network. Then, we designed two pretext tasks to formulate pseudo-labels for encouraging models to learn motion and appearance feature respectively. Next, we will describe the motivations and details of two pretext tasks. The first task names relative speed perception. This task follows the spirit of playback speed perception pretext task. However, instead of predicting the specific playback speed of each video clip, we sample 2 clips from the same video and train a neural network to identify their relative playback speed. This is because we observed that for the same video, the higher the playback speed is, the faster the objects will move. Thus, the relative speed labels are independent of the original speed of objects in a video. These labels can reveal the precise motion distinction between 2 video clips. In this sense, the labels are more consistent with the motion content and can provide more effective supervision for representation learning. Formally, we compare playback speeds of 2 video clips by maximizing the similarity of 2 clips with the same playback speed and minimizing the similarity of 2 clips with different playback speeds. We achieve this goal by optimizing a triple loss, where P+ indicates the dot product of 2 clips filmed at the same speed while P- indicates the dot product of 2 clips filmed at different speeds. The second task names appearance-focused video instance discrimination. In this pretext task, we tend to enforce models to learn appearance features. To this end, we observed that the clips sampled from the same video often share similar appearance content. Following the spirit in instance discrimination task in image domain, we enforce the model to find 2 same video clips from the other video clips. Finishing this task enforce models to discriminate the appearance distinction between clips. Moreover, to make models to focus more on learning appearance features, we propose a speed augmentation strategy. Specifically, we randomize the playback speed of each clip. The motivation for this strategy is that different clips in the same video are often filmed at the same speed. We randomize the speed such that models cannot find 2 same video clips by simply learning speed information. Instead, models are supposed to focus on learning appearance features to finish this task. Formally, we achieve this goal by optimizing an info-NCE loss. Specifically, we sample 2 clips from the same video. We consider one clip as a query and another clip as a positive key. The similarity between these 2 clips are denoted as Q+. Then, we sample K clips from other K videos and consider them as negative keys. We calculate the similarity between each negative key and the query, which is denoted as Q-. All clips are sampled at a randomly selected playback speed such that we enforce models to focus on learning appearance features. During the pre-training phase, for each pretext task, we use an individual projection head to map spatial temporal features to a new embedding spaces. We train models on these 2 pretext tasks jointly. The LM and LA denote the loss functions of each task, and lambda is a fixed hyperparameter to control the relative importance of each term. During inference for downstream tasks, we forward a video clip through the spatiotemporal encoder and obtain the corresponding video features. Then, we feed the features into a classifier to get the results of downstream tasks. We evaluate the effectiveness of our RSPNet on 2 downstream tasks, including action recognition and video retrieval. First, we conduct a ablation study on action recognition to verify the effectiveness of each pretext task. Then, we compare to the state-of-the-art methods on 2 downstream tasks. Finally, we visualize the activation map of the learned features to further understand the RSPNet. We pre-train models on the training set of the Kinetics 400 dataset and fine-tune our RSPNet on UCF101, HMDB51, and something V2 with labeled videos. To reduce training costs in ablation studies, we build a lightweight Kinetics 100 dataset by selecting 100 classes with the least disk size of videos from Kinetics 400. Compared with training from scratch, using the RSP or a vid task for pre-training significantly improves the action recognition performance on the UCF101 and HMDB51 datasets, which demonstrates that models learn useful clues for action recognition through pre-training on our designed pretext task. When we jointly pre-trained models on both pretext tasks, we achieved the best results for all three models. To verify the effectiveness of perceiving the relative speed of two clips, we replace the RSP pretext task with a speed prediction task. We denote the IT as SP. In the SP pretext task, we directly predict the speed of each clip. As shown in the table, compared with directly using the playback speed of each clip, exploiting relative speed as labels consistently improves the performance on 3 backbone networks and on 2 datasets. This demonstrates that relative speed labels are more consistent with the motion content and help models to learn more discriminative video features. To verify the effectiveness of speed augmentation strategy, we remove it from the AVID pretext task. We denote it as VID as it is not appearance-focused. As shown in the table, the speed augmentation strategy significantly improves the performance. The reason is that the speed augmentation strategy makes the VID task become speed agnostic. In this way, models are encouraged to pay more attention to learning appearance features. Together with the motion features learned from the RSP task, models can extract more discriminative representation for appearance and motion, which are both important for action recognition. Next, we compare our method with the state-of-the-art self-supervised learning methods. For fair comparison, we evaluate 2 settings. The first one is freezing the backbone and only train a classifier. We denote it as frozen. The second one is fine-tuning the entire network. We denote it as not frozen. Our RSPNet achieves the best results on all backbone networks over the 2 datasets under 2 settings. Remarkably, for action recognition on the UCF101 dataset, we achieve 93.7% accuracy without the use of labeled data for pre-training, which outperforms the ImageNet supervised pre-trained model. Next, we compare our RSPNet with other methods on video retrieval downstream task. Our method outperforms state-of-the-art approaches by a large margin under different values of K. This result implies that the proposed pretext tasks help us to learn more discriminative features for video retrieval task. Finally, we use CAM technique to visualize the region of interest for 2 pretext tasks. We observe that for the RSP task, the heat maps tend to cover the whole region of actions, which provides rich information for perceiving the relative speed. For the AVID task, models tend to focus on small but discriminative regions to identify 2 clips in the same video. One interesting finding is that the models are able to adaptively localize the same object even though they appear in different locations of a frame. This approach may provide a new perspective for person identification, which we leave for future work. In a conclusion, in this paper, we have proposed an unsupervised video representation learning framework named RSPNet. We train models to perceive relative playback speed for learning motion features by using relative speed labels to resolve the imprecise speed label issue. Additionally, we extend the instance discrimination task to the video domain and propose a speed augmentation strategy to make models focus on learning appearance features. Extensive experiments show that the features learned by RSPNet perform better in action recognition and video retrieval downstream tasks. Visualization of the ROI implies that RSPNet can focus on the discriminative area for 2 tasks. Thank you. For more information, please visit our GitHub repository.